Here we go. All right. Hope everybody's having a good week. We're, I guess, kind of halfway, I think. So I don't think there's much to say there. Just one announcement. The midterm should have been posted as of 2 minutes ago, assuming Blackboard is working today. It was not working on Monday. So if it goes down between now and next Tuesday, we'll make accommodations. But it's due a week from yesterday. So you have just under a week, 6 days, due by midnight. That's in part because I think we would like to try to present at least some aggregate data before next week's class. So maybe we can do that during the day. Fingers crossed. It is 20 multiple choice questions worth 10% of your grade. You may use your book in notes, but please do not consult with one another. We really want this to be your own work. It's a little bit of an honor system here because we're in an online format, but please do that. I imagine if you guys have been coming to these meetups, listening or watching the recordings and doing the labs, and I hope it's not a big surprise, or it's sort of just, I always view these as sanity checks. It's like another way to just make sure all the learning that we think is happening is happening. So we'll go over it next week. Hopefully next week, if not the week after. If I don't know how Blackboard works with these exams. It's the first time for both of us, right? Have you done this before, Angela? No. Yeah. So any questions about it at this point? I mean, if somebody just goes on real quick and make sure you can see it, there should be a midterm link on the left-hand side, and you click on it, you should be able to see all 20 questions. I think we configured it so you see all 20 at once. And like I said, we mentioned last week, there's no time limit, as long as it's submitted before Tuesday of next week.
Wait, where is it located on like the Blackboard?
It should be on the left-hand side. So let me see if I can do this. I won't click all the way through because I don't know what it will see.
There's no content to display. I don't know if that's what the person who also spoke sees.
Okay.
I got that too.
Okay.
We don't have that tab.
Item is hidden from students.
Why is that hidden? Okay, so I thought I had a view. So make available. How about that? So there's section 1. Let me go over to section 2. Well, I'm glad I brought this up. Can you see it now?
Yes.
Yep. Thank you.
Okay, great.
So do we get an extra day now?
We'll give you an extra 2 minutes.
Wait, if I click on it, will it like start the exam?
Yeah, but it's not timed. Like it's not. Yeah, you can stop and come back.
But
Wait,
you should not click on it now because we're
you're gonna listen
right now.
Yeah, you're gonna listen to us. But if you want to click it, just make sure you see the question. Yeah.
I just want to make sure if I click and like walk away, it won't like disappear on me.
Actually, I don't know. I don't know if there's a save button or not, but
I just started it, and you can save all answers or save and submit. So just as you go through, click save all answers, and you can come back to it later.
Thank you, PK.
Thank you, PK.
We're learning together here. This is great. All right. Let's talk about inferences for categorical data. So, it showed the answer right away. This was supposed to be a little quiz, but so let's just consider this little scenario. So we have, two scientists want to know whether or not a particular drug is effective against high blood pressure. Scientist A wants to give the drug to 1,000 people with high blood pressure and see how many of them experience low blood pressure. We have the second scientist who says, I want to give the drug to 500 people with high blood pressure and give the drug to another 500 people who also have high blood pressure. So the question is, right, what is the better approach to understand whether or not this drug is truly effective? And of course, everybody here knows that doing the 50-50, right? 500 get it, 500 don't, right? Randomized trial. So really what we want to do here, right? So this is a scenario that was presented to people, and we kind of get their response. Which scientists do you agree or just, agree with in a way to try to get to an estimate of how many people have good intuition in terms of causality, right? So that's what happened, right? So we have this general survey, GSS, which is actually something you could use for your data project. I don't think it's on the list, but I probably should have put it on there. But it's like a big survey that's given periodically on a whole host of topics. And so one year they had this one on drug tests to kind of get a sense. So out of 670 respondents, 571 had the correct answer, or right, had the correct intuition, and 99 did not, right? This is probably a common type of problem you have. You know, whether it's, you could do this with survey data or you could do it with any kind of count data, right? You have a good answer, a true answer, and a false answer. Or, you know, if you're looking at surveys, right, you could have how many people agree versus disagree, and is there a difference between those two, right? So this is the kind of problem we want to kind of solve. Is like, you know, two ways we could look at it is like, what is the estimate? Right? We want to say, what's the proportion of people who have good intuition about randomized designs? We are in the spring, but we'll probably quickly come up since we are in an election year, right? How many people, you know, support Biden, or we know what's the Democrats, right? So Democrat versus Republicans, right? Pollster kinds of things. You want to get an answer and say, you know, X%, you know, agree or are going to go for this candidate. And then we're going to have some kind of margin of error there. We want to know, well, that's what we got in this one sample, but if we did lots of samples, where would that be, right? Probably this should hopefully transition nicely to what we've been talking over the last 2 weeks. So in this case, right, previously we've really been focusing in on the mean as sort of our estimate, right? But now we just have a proportion, right? In this case, proportion that have good intuition. And so that's what we're interested in, right? But of course, what we have is the proportion from some given sample. And so really the key here is this, we use this little caret or hat on the P that indicates that's our observed or sample estimate. And what we're really trying to get to this. But there's nothing really terribly new here, right? We can use a confidence interval approach in the same way we did for normality, right? So we're going to have some point estimate plus or minus some margin of error. So we're just going to call it something slightly different, but it's very much analogous to the standard error that we use for continuous variables. What's different is kind of how we calculate this, because we're not talking about a distribution in the same way. First of all, we can't calculate the mean. So the way we do that is we take the proportion of success, and I'm putting that in air quotes, right? It's I'm going to use the word success and failure here, but you can interchange like option A versus option B, right? I know success and failure presumes one side has greater value than the other, perhaps, and it doesn't have to be that way, but that's often how textbooks write about it. And so I just want to make that clear. So we have the probability of success times the probability of failure over n, and we take the square root of that whole thing, right? So, well, let's just look at, all right, well, those are the, so in this case, we're going to take, 571 over 670 times 99 over 670 divided by 670 over n, right? That's how we would calculate the standard error with this given example. So why can we do this? Well, it turns out the central limit theorem holds for proportions as well as our continuous variables. So under the central limit theorem, what we could say is when our sample size approaches infinity, or as it gets larger, it is the estimate for the sample proportion is going to approximate the normal distribution with mean equal to that proportion, and this given standard error. So even though we're dealing with proportions, it turns out that the standard, the sampling distribution of proportions is also normally distributed, right? But that distribution, because we don't have a standard deviation in the same way, we kind of define our standard deviation this way. So the standard deviation for the sampling distribution for proportion turns out to be this, okay? A couple of conditions that have to be met: independent observations, meaning each respondent is independent of each other response. And we'll talk about that a little bit more towards the end of the class. And you need at least 10 successes or failures. So this is analogous to you need a sample size of at least 30, right? It's kind of the somewhat arbitrary, but pretty good threshold that we use for continuous variables. we'll relax that sample size next week for continuous variables. So just working out the arithmetic then for our example. So we had 85% of Americans answered the question correctly on quasi-experimental design, right? We want to calculate a 95% confidence interval, which is often, the common one we're going to use. So here are our givens, right? So we have our n, and we have our proportion, our probability of success here, which is 0.85. So let's check our condition. Independence. So the sample is indeed random, right? It's a random sample, and 670 is less than 10% of all Americans. The reason why we have this, and again, I have another slide towards the end, is as the proportion of our sample gets above 10%, this independence assumption is clearly going to be violated in some capacity. And I actually have some simulation data that shows why 10% is chosen. Our success failure rate, right? So we have 571 that answered correctly and 99 that answered incorrectly. So clearly we meet this. So we have a sufficient sample size, right? And so we just run this through. So we're using 1.96, same critical value, because it's going to follow the normal distribution. So we end up with a confidence interval between 82 and 88%. So what are we saying? So we're 95% sure that the true proportion of Americans that have good causality notion is somewhere between 82 and 88%. Okay. So sometimes you can, divide that, and a lot of times you'll say, oh, well, it's 85 plus or minus 3% or so, if I'm doing that arithmetic, because it's 3% on each side. Right. So why 3%? Right. This just turned out to be 3%. And so as you start looking at polling information over maybe even now as it starts to come up, pay attention to the sample sizes they use, right? And so for many, for a whole host of reasons, some of which I'm not entirely sure, some is arbitrary, some is because when you want to make the standard error smaller, that growth is not going to be linear. So most pollsters try to achieve like a 3% margin of error, plus or minus 3%. Well, why is that? Well, let's consider the numerator here. If we look at the numerator, in order to get that as large as possible, right? If we took 0.5 times 0.5 of all the possibilities, that's going to be the largest numerator we have. So we have 0.4 times 0.6, right? Because the sum of those two values has to equal 1. So to make that as large as possible, that's what we're going to assume, 50-50. That's the worst case scenario that will result in the largest standard error. So that's why I'm using that. And so if we want a 3% margin of error, well, we can just use this formula. We're just fixing the left-hand side. That's what we want. And so we want to solve for n. And so we just could do the arithmetic. And so in order to have a 3% margin of error, we need an approximately 1,068, a sample of 1,068 to guarantee at least a 3% margin of error. Now, of course, if your observed proportion is like 40-60, 30-70, something like that, your margin of error is going to be smaller. But if it ends up being 50-50, it would be no greater than that. Now, it turns out, and you could do this on your own, say you want a 1.5%, you want to cut this in half, you're going to need you're going to need your sample size not to be double. It will actually work out to be like you need like 10,000. A sample size of 10,000. So this is where there's a balance, like how specific or how narrow do you need to be versus how much sampling do you need to do to get that standard error smaller. Okay, that's one proportion. Well, what if we have two proportions? So this is a separate question also from the GSS survey. Scientists want to predict global warming and survey people on, how they think global warming will impact the polar regions in the next 100 years. One of the possible effects is that the northern ice cap may completely melt. Would this bother you? So they asked them a great deal, some, a little, or not at all. And so we have the results from the GSS, but then also surveyed students from Duke University. Okay. Why Duke University? Well, that's where the author of the textbook was at the time that she wrote this. We should survey CUNY students at some point. So you can see we had 680 GSS and 105. And so the question we're going to ask, we're actually going to simplify this a little bit. So we're just going to say, we want to know, is there a difference between the American population at large and Duke students in terms of thinking it's a great deal? So we can dichotomize this one in this case, right? So that's our parameter of interest, right? Duke students minus all Americans. And so what we're actually going to have is the proportion from Duke and the proportion from US. And we're going to set this up as a null hypothesis test, as we have been talking about, right? So again, we have some point estimate. In this case, it's a difference of two proportions, plus or minus some margin of error, right? And remember, we can, our hypothesis test, right? So we're gonna have some z-value. So we have the point estimate minus some null value. In this particular example, our null value is 0, and it is often 0, right? We're trying to test that the difference between two groups is 0. But I like to be explicit. That doesn't have to be 0, right? But that often gets dropped once it's 0, right? We just say point estimate over standard error, but just do remember that null value is really up there. So of course we have to have a slightly different formulation for the standard error because we got two proportions. And so we're just extending it out. So we're looking at the proportion for group 1 plus, the proportions for group 2. And so we have separate sample sizes. And so that gives us the standard error, which is the standard deviation of the sampling distribution for the difference of proportions. Still, so the success failure is exactly the same, right? We need to have 10 success and failures in both groups, right? We just got it in each group. Sufficient cell sizes is often how we might refer to it. Independence, we kind of got to break up in two ways. So we want independence within groups, okay? So the US group is sampled randomly in the Duke students, right? And they're each less than 10% of their respective proportions, okay? That's all good, right? I think we're fine. We randomly sampled. One person's response isn't going to influence another, okay? But independence between groups gets a little tricky here too. So in this case, we're going to presume Duke students are separate from US students, but you need to recognize that this is technically not true because many Duke students are Americans, right? They're a subset of the other group, okay? And so you need to be careful when you define this. So really what we need to say here is the difference is between Americans except Duke students and Duke students, right? But it turns out the proportion of Duke students to all Americans is so, that ratio is so large as to be almost inconsequential mathematically. So we're going to ignore it, but be careful if you're in situations where you're doing a comparison between group A and group B, where group B may be a subset of group A, because you are indeed violating that independence assumption. But if the ratios are not too bad, you're probably okay. Okay, so let's run through some arithmetic. So like I said, we simplified the table here. So we're looking at a great deal and not a great deal. And so 65.7 Duke students said a great deal, 66.8 of the US population said a great deal. Are those differences statistically significant? This just turns out to be now a simple algebra problem, substituting that in. So here's the difference in our two proportions. 1.96 is our critical value for a 95% confidence interval. Roll this all out and we end up with a confidence interval of negative 0.108 to positive 0.086, right? And since 0 is within the interval, we would fail to reject the null hypothesis here, right? A difference of 0 is a possible outcome within our 95% confidence interval. Questions about that?
Can I ask a question on this one because I sometimes I get confused. I got from the information that you send us that if we're doing confidence intervals, we're supposed to use the actual proportions that we saw in the two samples, right? Of the two proportions, right? So you can hear P of Duke and the P US. But if we're doing hypothesis test, we're supposed to get the blended because the hypothesis is that the proportions are the same, correct?
Yes. The difference
So
is
in
0.
this case, but in this case, you ended up, I still, what I'm trying to get is, in this case, even though you're doing hypothesis tests that they're the same, you still use the different proportion. Why is that you didn't use the blended if you're trying to test that they are the same?
Let me see. I'm not sure if the difference between the two proportions.
Because I mean, I understand like this, right? That if you are doing confidence intervals and you have two proportions, you're supposed to use the observed proportions of each.
Yep.
But
which
if you're
we
doing
have right
hypothesis
here.
tests and your null hypothesis is that they are the same, then obviously the null hypothesis, you cannot use different proportions, right? Because you're testing that the proportion is the same. So you should use a blended proportion, right? To test the hypothesis.
Well, it's the difference, right? Because if the proportions are the same, which is what we're testing,
yeah,
we can get to it. So if the proportions are the same, that means the difference between the two proportions would be
zero. Yeah.
So we're recentering, you can think of it as recentering the sampling distribution around the differences of proportions. Where if you use the blended, then you're trying to compare two distributions and how far apart they are, which I have to think about, but it just arithmetically makes a lot of, it just makes more sense to just look at a single distribution of the differences of the scores. I feel like I'm not helping.
Yeah, because the reason is because there was another comment that you made in the summary where basically you explain that. Let me pull exactly what you said, right? So basically you're saying, I'll read it, for confidence intervals and hypothesis tests where H0 is P1 minus P2 equals some other value than zero. I understand that one, right? But when you do confidence intervals, you have to use P1 and P2s, right? The two proportions.
Yep.
And you say hypothesis tests when P1 and P2, the difference is equal to zero, you have to use the pool, the blended proportion rate success.
Which slide are you looking at?
I'm looking at the summary you put of chapter 6, the learning outcomes.
Oh, I see what you're saying. Yeah.
And there was something that you mentioned which I couldn't understand. And actually that piece, I think I understand it. Maybe not understand it, right? But then you said such discrepancy doesn't exist when conducting inference for means, since the mean doesn't factor into the calculation of the standard error what the proportion does. I couldn't understand what you mean with that.
There's a typo here. Oh, sugar. Okay. Good catch, Juan. No one's caught this before.
Sugar?
Yeah.
Okay,
it's being recorded. I got to be careful. Okay. I need to make a note. This should be 1 1, right? And this should be 2 2. Oh, wait a minute.
Because it looks like you're using people, like I was saying, blended rate. And I thought it makes sense, because if you're talking that the hypothesis test is that they're both the same, then you should blend the rate, right? Because you're assuming that the proportions are the same for both populations. So that's what I understood in that pool.
Yeah. No, you're right. I'm gonna punt on your question just for a minute.
Okay, no, that's okay.
I'm gonna come back to it.
Yeah,
because I gotta work it out. But
actually, what I was mostly interested in the other piece where you said that this doesn't apply to the means because it's not in that comment completely threw me off. I couldn't understand what you were trying to say there.
Oh, I don't know. It's akin to, it's like analogous to the means that we talked about with quantitative. So when we talked about the central limit theorem so far, we've dealt with like continuous variables, quantitative variables, right? And so the estimate of interest is the average or the mean of that group. So in the case of proportions, or when we're categorical variables, the proportion is, we use the proportion in the way that we use a mean in a quantitative variable. So it's kind of a measure of center. Right. And the standard error is our measure of spread in the way, the margin of error, which is the standard deviation of the sampling distribution for a qualitative variable, is analogous to the standard error, which is the standard deviation of the sampling distribution for a quantitative variable. So I need to make where did my pen go? There's one. I need to make a note. So quant qual center. I'm going to create a table. I think a 2x2 table, just to kind of clarify this language, where you could have quantitative, qualitative, measures of center, measures of spread.
Okay.
Right. And in the terms of central limit theorem and null hypothesis testing, what we're really interested in is the differences in our measures of center, which is the mean for a quantitative variable, a proportion for a qualitative variable. And in order to test whether or not they're different, we need a measure of the spread of the sampling distribution. For a quantitative variable, we call that the standard error. For a qualitative variable, we call that the margin of error. But realize those are both describing the sampling distribution. And from the central limit theorem, what we know is the sampling distribution is normal. And because it's normal, we can use, right? So if we want a 95%, well, we know if we go 1.96 units above and below the center of the distribution, we get 95% of the area under the curve. Is that helping?
No, it does. It does.
Okay.
I think actually that table, I think, will become handy because I'm still trying to figure out. I think I got it. When you do a hypothesis test and when you do versus you're doing confidence interval, it should be independent of a null hypothesis. You're just saying, I feel confident that the true value lies between these ranges.
Yeah.
A hypothesis test, you're trying to prove or disprove, right? Disprove.
We, as a statistician, we avoid the word prove.
We're prove. Yeah, we're trying
to show evidence of.
Yeah. We're trying to infer, right? We're trying to infer something. So okay, I got it. And I think the table that you mentioned is going to be handy. I think. Thank you.
Okay,
sorry to deviate you from your.
No, not at all. Not at all. Because if you have this question, I bet you I confused other students. So I always welcome it. That'll be a quick little thing just to kind of orient the language, I think, between quantitative and qualitative variables. I never really kind of thought of it that way. Like in my mind, I've been doing this so long. So it's like, we're just taking the central limit theorem that we've been doing, and now we're applying it to the notion of qualitative. And sort of these properties are still there, but now I'm wondering, like, it's interesting because this week and next week used to be, in the previous edition of the book, were reversed. Inference for quantitative came before qualitative, and I'm going to come back to you. I might even put you on the spot, Juan, after we do next week, to say, would it have been easier to hear next week's lecture before this week? Because some of those issues that transition from the difference between two groups in a paired and unpaired way, kind of, I think, more naturally leads into this notion. And then when you get to proportions, it could be easier. I may just flip that back. But it's tricky because in some ways this is a little less, well, actually, probably the better thing to do is do the basic null hypothesis testing. Well, I'm going to give away the t-test, right? That you may have seen, right? That's everywhere. Do that, then do this, and then do the rest. The problem is the quantitative chapter also, when you get to multiple group comparisons, gets quite a bit more complicated. So I might even rearrange these two chapters. So Angela, we should probably talk about that. It's actually, this might be a good, I'm glad this came up. So I want to make sure next week to do a full recap of these two chapters together, because I think that will be very helpful. All right, let's look at another example, unless somebody else has another question, just chime in. I love this example, particularly if you like gambling or you do any games with dice, right? So, and I also find it absolutely incredible what people did to get data prior to now. I think as data scientists, we need to be reminded that data was not always readily available. And a lot, and actually, I think nowadays it's interesting. I've followed this economist, and he often talks about like what makes some of his papers more interesting is that he actually puts legwork in to try to get data from different sources, and in interesting ways that are often not readily available, and you can get some really keen insights. But so Weldon So in the late 1800s, early 1900s, he was an English evolutionary biologist, also considered the founder of biometry. He was also the founding editor of Biometrica with Galton and Pearson. So Pearson's probably a name you might have heard of already. Galton is someone else you should probably have heard of. Biometrica is one of the top, if not the top, sort of methodological journals. A lot of seminal papers, particularly in statistics, were published there over the last century and a half or so. So in 1894, right, he rolled a dice, 12 dice, 26,306 times, and recorded the numbers of 5s or 6s, which he considered to be success, right? So there's a expected 1/3 probability of success, right? If it's a fair dice. So just imagine in 1894, I wonder if he had grad students to roll 12 dice that many times. So, and what he observed though, is that 5 and 6s occurred more often than expected. And so Pearson hypothesized that this was probably due to the construction of the dice, right? So inexpensive dice, you just kind of hollowed out the pits to kind of put markings for how many, what side that is. And so since sides opposite add to 7, face 6 pips is lighter than the opposite face, right, which only had 1 pit, right? So the opposite side of 6 was a 1. And so if you only took 1 pit out, there should be more mass on that side, which should then change the probability. So that's what Pearson. And so I love this because this is, these are the kinds of problems people were working on that gave rise to all of these methods that we use now for all sorts of crazy things, right? So then Labby in 2009, he's at the University of Chicago, repeated his experiment. But he created a machine to do it, to roll the dice and do it. And there's a YouTube link, you can watch it later on how the machine works. So when Labby did it, right, he was able to do each roll or image processing took about 20 seconds per roll. And so each day he had about 150 images. So it took Labby with the machine 6 days, right? And I just want to take a moment and reflect, like, how long did it take Weldon to roll 26,000 dice and record it? Anyways, and there's another paper here you can look at, and this is the distribution of the dice, the die face. So we could see here that 1 and 6 actually occurred more frequently than the other 6 sides. And so this is kind of I know this seems kind of arbitrary, but think about this for a second. This is often a problem we encounter in data science and broadly in statistics. What we want to test is we have some expected outcome. We have some sense of what the outcome should be. And then we observe something. And what we want to know is what we observed different than what we expected. Okay. This is kind of a way of thinking. One term we're going to start using is like model fit, right? In data science, you're going to train lots of models, and we can have certain expectations of how that model would perform. And with new data, we want to know, does this model fit or not fit, right? Our null hypothesis is, does these data fit this model in a way that we would expect? So this kind of notion here, very simple, will over the course, not too much in this course, but in future predictive modeling courses, will expand quite a lot. And so we can write this out as a table. Right. And this is often how these problems are presented in various ways. So we have our observed column and then our expected. So you can see an expected with 315,000 dice observations. We would expect 52,612 of each 1 through 6 occurring. And then on the left side, right, we have what we actually observe. So the totals are the same. We fixed it that way because we kind of have this sort of expected outcome. This is a null hypothesis test. It's kind of how we're going to structure it. So what we're saying is the null is that there's no difference between the observed and the expected columns, right? So then the alternative is that there is a difference, right? That the observed counts do not follow the same distribution as the expected counts. And in this case, we would probably conclude that there's evidence that the dice are biased and not fair. So to evaluate the hypothesis, we're going to quantify how different observed counts are from expected. Large deviations, right? The same notion we've been talking about, starting with coin tosses. How many more heads and tails do we need before we go suspect that the coin is biased? How many more ones and sixes or twos that we need before we can say it's? So we often call this a goodness of fit. How well do our data fit the model or the expected distribution? So again, here's our general form. We have a point estimate, we have a null value, and we have the standard error of the point estimate. The construction of the test statistic is based upon identifying the differences between a point estimate and the expected value, and then standardizing that difference using the standard error on the point estimate. Right. So the reason why we're dividing by the standard error is now we have a standard score, right? In the same way we had z-scores, right? We did a z-score conversion. This will ensure that we standardize that distribution. And then the result of this is going to be our test statistic. Okay. Now, this is our first introduction to a test statistic, I think. It turns out in this case, because we're talking about count data, right? And the way we're calculating sort of this test statistic, right? So we're going to have observed minus expected squared over the expected value. Okay. Couple things to note right away. And we're summing that across all our cells. So we have K cells. And we call this particular test statistic a chi-squared. Okay. Note, we're taking the difference and then squaring it. So the numerator is always going to be positive, and so is the denominator, right? So as a result, this quotient will always be positive. So we're summing a bunch of positive numbers, meaning our test statistic cannot be less than 0. And that's kind of important. So we've talked about null hypothesis tests in terms of two-tailed tests. We're now going to talk about a test statistic that is always going to be a one-tailed test, because the distribution is going to have to be bounded at 0. Okay. So if we work this out, right? So if we take observed minus expected, so we have 53,222 minus 52,612, square that, divide by the expected value. And for the first row, we get 7.07, right? All the way down. So you could see just intuitively, right? If we go back to the bar plot, right? So 1 and 6, right? So this dashed horizontal line is our expected value, right? And so we're looking at bars that are further away, right? The further away bars are from this line, the bigger we want this contribution to our test statistic, right? And actually we want that contribution to be nonlinear, which is one of the reasons why we square. We square for 2 reasons. One, right, it makes all the values positive, which has some arithmetic advantages. And 2, it means the further away points get away from the expected value, the more they contribute to the sum of all of those differences, right? And so if we look at this, right, what are the large ones? 7, outcome 1 and outcome 6. And looking at this, so here's outcome 1, right? We're taking the observed minus the expected, squaring it, the observed minus the expected, squaring it. And those are some of the larger contributions. 2 is also quite large, right? So then the chi-squared, if we sum this column, is 24.73, right? So this does not follow a normal distribution. This follows something called a chi-squared distribution. And we're going to learn a couple of different distributions as we go through. We'll learn a couple of new ones next week as well. So by squaring the difference, it does 2 things, right? Standardizes the difference, so it's now all positive, and the differences that already look unusual become much larger after squaring it. And that's both these things are properties we're going to leverage a lot in statistics on how we estimate some of these things. But there's this additional component now that we want to take advantage, that we're going to leverage to determine this distribution. So there's not a single chi-square distribution. There's a whole class of chi-square distribution, and they're going to differ based upon the degrees of freedom. Now, for now, it's okay. You can just conceptualize it. Degrees of freedom is really typically going to be defined as the sample size minus 1. Okay? I always like to think about it, right? So if I have 10 observations, right, I have 9 gaps, right? From first to the second, second to the third, right? So that's why it's always -1. So degrees of freedom, something we're going to leverage for a while. For now, just know it's typically n-1, right? And so here I just drew 3 different chi-square distributions. So this blue line is with 2 degrees of freedom, right? This green line is 4 degrees of freedom, and this red dashed line is 9 degrees of freedom. So first thing, right, to recognize is just kind of get a sense of the area, right? So if we had only 2 degrees of freedom, right, and we want to get 95% of the area under this curve, right? I should make clear that the area under all of these distributions is equal to 1. So we're interpreting the area in the same way we did with a normal distribution. But now we're going to put our 5%, if we want a 95% confidence interval, we're doing a one-tail test. So we just want 5% of the area to the right. Well, to get 5% to the right with 2 degrees of freedoms, right, is probably, I don't know, maybe somewhere around here, right? When we get up to 4 degrees of freedom, right, so this would be our critical value. This is what our chi-squared would need to be to reject it. When we get to 4 degrees of freedom, well, 5%, I might be maybe a little bit more out here, right? I need a larger test statistic. Oops. Go to 9 degrees of freedom. Now I'm even further, right? So the more degrees of freedom, the larger your test statistic needs to be to reject. So working through this particular example, right? So our degrees of freedom is because, well, K being number of in this case, it's number of cells, right? So, oops, our degrees of freedom here is going to be 5, okay? Because we have 6 outcomes. And our test statistic, we already calculated, was 24.67, right? So if we take the area of 24.67, which is somewhere around here, the area to the right is less than 0.001. So we would reject the null hypothesis here and suggest that the dice are indeed biased. Okay, so it is true that the 1 and 6 axis is consistently shorter than the other 2, thereby supporting the hypothesis that faces of 1 and 6 pips are larger than other faces. The Pearson's claim, however, did not hold up. And if you're thinking of making a trip to Atlantic City or Vegas anytime soon, realize that now casinos fill the pips and do these same kinds of null hypothesis testing to ensure that the dice are in fact fair and evenly balanced. So, all right. So to recap, so p-values for chi-squared. So here's one kind of chi-squared. Chi-squared's bounded at 0. So we're always looking for the p-value to the right-hand side. All right, we got about 15 minutes. Good. Questions about that before I go on to one other little quick topic?
Is there a connection between chi-square and the variance?
So variance is a concept very specific to quantitative variables, right? So there's not really a definition of variance for qualitative variables. We tend to just use the margin of error, which is really it's the standard deviation of the sampling distribution. So if you squared that, you would have the variance of the sampling distribution. So we don't really have a sense of spread in the way, because in the case of a quantitative variable, we have values that can be anywhere around the center. For qualitative variables, like if we just take the survey, right, or if we go back to the experimental design, right, we code it in R as either 0 or 1. There's only 2 possible values you're going to see in your data set. It's either 0 or 1. So R will give you a variance, but it's not really meaningful. So it doesn't work out because it's just becomes a count of how many zeros and how many ones do you have. And sometimes we call the 0 failure. Sometimes we call it and 1 true. Sometimes we could say, and then when we get into the regression, we'll talk about how we code qualitative variables into 0 and 1s. So 0 could be male and 1 female, right? They could just mean different things. It doesn't really have to be success or failure. So there really isn't a variance, a counterpart to variance for qualitative variables. Does that make sense as to why?
Yes, thank you.
So I followed you up to the, I understood the degrees of freedom.
Mm-hmm.
And then how you use the degrees of freedom to find the goodness of fit, you lost me.
So it's just in the.
So I got that, but
yep.
here.
Yeah.
Right.
Okay. Right. Okay, we're gonna have to do it this way. So let's. So if we go to R, let me create a new R script. Uh-oh, I can't see it. All right. Oh, I guess it did pop up, and I'm gonna restart my R session. Okay, so the so we're gonna do a little bit of live coding. Let's see how this works out. So I'm gonna do X is gonna be a sequence from 0 to, let's go to 25, step equals 0.01. Okay, so I have, wow, that, I don't think that's exact. I did that wrong. Sequence, it's not, I have the wrong parameter name. Oh, it's by. All right, so if I do by, okay, great. 2,500, X's. That's all I really want. All right, let's look at, I think it's chi-square. Oh, there's a chi-square test, but oh no, I want d chi, I think. Oh, it's d chi-square. Yeah, okay. So I think last week we talked about, we had d norm, p norm, q norm, r norm. Now we have, I'm going to look at d chi-squared. So if we look at the documentation, so remember, d is going to give me the height of the distribution. Notice we have this additional parameter here called df, which is degrees of freedom, right? So it has to be a non-negative value. So what we can do here, and I'm just going to do this in base R, I'm going to plot x against d chi-square with x and degrees of freedom if we start with 2. Right, this is what the chi-square distribution looks like. So now if I'm just going to double it. I'm going to go to 4, 6, 8, right? 10. Okay, right. You see how the shape is shifting? So what is actually happening? So let's use the other function. So let's say, let's do us. I'm going to call it critical value is going to be sequence. I want to go from, let's say 2 to 25 again, but by 1, right? So actually that's not, I'm just going to call it degrees of freedoms, right? So let's say I can do p chi-squared, no, not p, I want q, yes, q chi-squared, okay. If I had 2 degrees of freedom, no, I want 0.5. And if I said, if I had 2 degrees of freedom, is that right? I have to go back to my slides from last week. I'm trying to, Angela, can you help me out here? Do you know what, what's that? Was it in this one? Where's that plot that has the relationship between the PQs, Rs? No, not that one.
I think it's distributions, right?
Is it the distributions one?
Look.
No, here it is. Okay. All right. So what I want is, actually, I probably could create this for a chi-squared. So I want to know the critical value. So yeah, I thought I want the Q. given a particular. Oh, I know what the problem is. All right, it's to the left. So this should be 0.95. No one reminded me. I think I said this 100 times and I even forgot it. So, let that be it always gives you the area to the left of the value, right? All right. So if I had 2 degrees of freedom, right, and I wanted a 95% critical value, my chi-squared needs to be 5.99, right? So let's do this so we can do chi-squared 0.95, and I'm going to do DFs. Will that work? Yeah. So here we go. So if I plot degrees of freedom against that, so we get a plot. So we could see here's 2 degrees, 3, 4, 5. This is the critical value we would need to reject the null hypothesis. So going out to 25 is not enough. Let's go to 1,000. Let's go. Actually, it does grow linearly. That's surprising to me. But so the degrees of freedom. All right. So for now, Diana, I think what I conceptualize that, right? If we go to the formulation, okay. Okay, so as we increase the degrees of freedom, we are pushing where the critical value is further out. Okay, so it's kind of a penalty for sample size or smaller sample sizes is one way to think about it, right? So it's the degrees of freedom is the way we can include, right? So when we had
I understand the theory, but then like you did some so I get that the more degrees of freedom you have, the further out you have to go before the area under the curve is 95%.
Okay.
Right?
Yep.
But then you say, okay, so this shows that the dice is weighted. And I was like, okay, but what did you do with the 24.67 to do that?
Okay, so
that's the part we
I gotcha.
What happened there?
Yeah. So what we could do here is can we just call it 24 or I guess 25? Right.
Whatever.
So what we did, so what we're looking at is so we had 5 degrees of freedom. So this is the chi-square distribution we're looking at. Okay. So if I do Q, no, in this case, I want P chi-square of 25. I mean, let's be precise, I guess, 24.67. So if you look at this later, it matches the slides, right? With degrees of freedom equal to 5, the p-value, right, to the left is 99.99. So because I want it to the right, I can take 1 minus that. So that's the probability. And since p is less than 0.05, right, for using the p-value approach to null hypothesis testing, since it's less than 0.05, we reject the null hypothesis. What was our null hypothesis? That all the sides are equal, have equal likelihood of occurring. And this suggests that no, the sides don't have equal likelihood of outcomes.
Thank you. That's what I needed.
Is that what you needed? Awesome. Got there. Long way to get there, but we got there. All right. So I'm just going to kind of blow through this a little bit. I'm not going to. So I mentioned this notion of independence between groups and, why 10%? Okay. So if we're going back, so I'm going to presume we have a population of 100,000. And we're trying to check whether or not A and B are independent, okay? And I'm going to stipulate that the proportion for group A is 0.55, and the proportion of group B is 0.6. The N for point A is 99,000, and the group size for group B. So if we want to use the Duke American thing, I'm saying we have 99,000, right? We have actually 100,000 American, 99,000 of whom are Americans, but not Duke, right? And 1,000 are Duke, but they're also Americans, right? So, but we can kind of separate them this way. All right. So in this case, what I'm saying is they're 1% of the population, the total population. All right. So what I'm going to do, right? And so here I just set those values here. And this is my total population size. So here I'm going to create a data frame in order for me to sample, right? So what am I going to do? I'm going to create a group variable. So I'm going to have a data frame called pop for the population. It will eventually have 100,000 rows. So I'm repeating A, 99% times the population N, right? And B, so I have A and B as my group variables. So it might be worth actually investigating this a little bit. Some of you might be interested in the R code. So if I do this, we run that, just so you can kind of see what's going on here. Okay, and then so I create population. So you could see population has 100,000 records. So we could see A, and we go through, and the response is 0 or 1 is set up such that if I do table pop group by response, right, I get this. But if I do prop.table, right, we get roughly 53%, right? So to whatever my stipulated proportions of success, 55 and 60% is what I was going for. All right. And then I'm going to pull these out as separate. So we could see here the mean for sample A is 56%, meaning the proportion of success 56, which is pretty close to my 55 that I stipulated. So this population of the sample excluding group B is 56, pretty much the same. And then the population for group B sample is 63%. Okay. All that to set up so I can draw this. So what I'm doing here as we go from left to right is I'm drawing a bunch of random samples as I would, right? So each dot here is a random sample of, I don't remember what size, 30, call it, right? Starting on the left where, okay, so the red line for those is the average proportion for group A excluding group B, okay? And this one here is just group B. And then the A is when I sample with group A, but not excluding. So the way to think about this, right? So this would be like the US. This is Duke, right? And I just do, and this green line is I'm sampling, well, this red line is I'm sampling from the US, but explicitly excluding Duke students. And this green line would be like, I'm sampling Americans, but I'm not checking if they're Duke students, okay? And I'm stipulating there is indeed a difference between Duke and US students. So as the proportion of those groups, right? So technically this red group is a subset of this purple group. So as the proportions of that subset group get larger and larger, right? What did we say? 10%, right? This is where the textbook tends to say. So without going into too much details, these are called lowest regressions. We'll talk about it later in the semester. These grays are 95% confidence intervals. So look right here, right about 10% is where those 95% confidence intervals no longer overlap. Meaning once we get above 10%, the not adjusting for that independence problem, because there is dependence in the sampling, is actually going to have a statistically significant effect on your estimates, okay? So be very, very careful about this, because I see data scientists do this all the time. So where would this occur? This actually occurred frequently in the education world. So we want to know, well, let's take our program. We want to know if our MSDS students have higher GPAs than CUNY more broadly, or maybe at the School of Professional Studies. The problem is the mean for CUNY SPS includes MSDS students, but then we're comparing it with MSDS students, right? So you're a proper subset of the CUNY population. But as long as the MSDS is smaller than 10%, of the total population, the super group from which you belong, and that's who you're comparing to. As long as it's less than 10%, the difference or the bias in that estimate is going to be not statistically significantly different. So in my prior work, like we wanted to compare programs, but we had some programs that were one program that was 40% of the student population. So really what you want to do is say, well, we're going to take that program versus all the other programs and actually exclude it to actually do it properly. And this is true. Yeah. So this is like comes up when you're doing population stuff. So in data science, we often do that. Anyways, so this is my warning to you that so what ends up happening a lot of times is you might not like if this I made this difference large so you would see it, but if the difference is smaller, sometimes you would fail to reject the null hypothesis that you should, right? It could cause you to, in this case, this is where a type 2 error rate might be more likely to occur. All right. 902, we did pretty well. I'm going to copy this link, put it in here, but I'm happy to answer other questions.
Do we cover T-score next time?
So next week is, t-tests and ANOVA. Let me check the schedule. That is right. So, yep. And then we're into linear regression. And for some reason, where spring break is like 3 weeks before the end. I don't know why they do that, but they did. No. Okay, good question. So the midterm covered topics up to last week, up to I lost count of chapter numbers. Inference, the foundation for inference. So this week on will be part of the final. 5B, thanks. Reach out to us privately on Slack if you have any issues with the exam. If it's a technical issue, like not showing up for you, you can, just make sure reach out to us. All right. Well, then, if there's no other questions, have a fantastic week. Try to enjoy some of this nice weather we're finally getting. If you're in the Northeast New York area, it's lovely today. All right. See you next week.
Thanks.
Thank you.
Thank you.